let's talk about the relationship between light and energy. So every single wave has an amount of energy associated with it, and we can calculate that. Let me show you the relationship, number one, and then number two, I'll show you the formula. So here's the relationship. You'll recall that if we have a very small wavelength, and I'm going to put gamma as our extreme example, okay, very small wavelength, that means you can fit a ton of waves in 1 second as a high frequency. Well, because you can fit so many waves in that 1 second, this also has a very high energy. Look at this relationship. Of course, we've got the indirect relationship between small wavelength, high energy, but check out this. It's a direct relationship. As you have a high frequency, you also have a high energy. So this gamma radiation, that's why we use it in cancer. It can literally explode, for lack of a better word, obliterate cancer cells. That's why we use radiation, gamma radiation, with cancer treatment. Now the reverse of this, if you have a very large wavelength, our extreme example for the electromagnetic radiation is going to be the radio, really huge waves from crest down to the next crest, really, really large. Can't fit very many of those in 1 second. So it has a low frequency. So huge wave, really low frequency. You can predict it. What would you say is the energy associated with this low frequency? Low energy, low energy. Now the only relationship that I haven't been explicitly pointed out is energy and wavelength. As you have, let's say, a really large wavelength, just the opposite, indirectly related, you're going to have a very low energy. So there's the thought and the relationship between wavelength, frequency, and energy. Now putting this into a formula, we have E equals H times nu. So let's label everything on this. E stands for energy, and there's something super important on this. It is the energy for one photon. That is important, for one photon. So this is where AP, not that they'll trick you, but they'll test if you're paying attention to detail. They'll give you energy in kilojoules per mole. So you're going to have to convert the energy into per photon, and you'll just use Avogadro's number for that. That's it. In fact, I'll show you that. So remember, this is for one photon. Our unit on this is joules. Okay, our unit is going to be joules. Now H is a constant. It's called Planck's constant. Pretty brilliant. Planck's constant. Again, if you're in an AP class, this is on your AP reference. It is 6.626 times 10 to the negative 34 joules times seconds. Joules times second. And then you recall, you know this, frequency is nu, our Greek symbol nu, and the unit on that is per second. For just a moment, look at units with me. We've got joules equals joule times second times per second. You can see the second will cancel and joule equals joule. So that's how the units work out on that. I want to show you quickly, if you are given energy in the kilojoules per mole, how you convert that. Kilojoule per mole, because it needs to be, if we're going to use this formula, it's going to have to be in joules per one photon. So I'm first going to convert from kilojoules to joules. There are 1,000 joules in 1 kilojoule. Next, 1 mole contains 6.022 times 10 to the 23 particles, and the particles we're talking about are photons. So let's say that you're given an energy of 37.2 kilojoules per mole. You would times by 1,000, divide by Avogadro's number, and your unit would be joules per 1, joule per photon. And that's exactly what this formula is. You could then plug that number in there. If you plug in 37.2, you're not going to get the right answer. It has to be per 1 photon. Super important. Nice. Good work. Bye.